Hello, and welcome to our finals week dead day edition of Mechanics of Materials. I've got my coffee, I've got my whiteboard behind me, I'm ready to go. Before we get started, I'm going to pose a question to the audience. What do you think the following situations have in common? An eye-bolt hook supporting a cable, a crane lifting a beam, a road sign subjected to wind, and a woman walking her dog. If you've been showing up to class and reading chapter 8, you know the answer to this. The answer is these are all situations of combined loading. But how did we arrive at chapter 8? How did we arrive at combined loadings? Well, the simple answer to that is the entire Mechanics of Materials book. But we're going to break it down into steps for you before we go into some more complicated examples of combined loading. So to start off, the simplest form of loading can be your axial loading. So if you have a cross section that's being loaded with some force P, you will have a stress distribution. Let's draw our stress distributions in a different color. How about? So we have our pipe. Pick this up. Being loaded with some force P. You can call it F, you can call it P, whatever you're more comfortable with. We have some stress distribution. We'll call stress, sigma, is uniform throughout the cross section of the beam. Right? That's the simplest form of loading, the simplest form of stress distributions. If you were to draw a QB at this point, you would simply draw stress coming out like that. Okay? So the second form, let's talk about torsion. How about? So we have a pipe that's being subjected to torsion. So what does our stress distribution look like? Well, if you remember from our earlier sections, the shear stress is the highest at the outer section. So your shear stress distribution would look something like that, and we can call that tau. And if we were at some little point here, our QB would have stresses that look like that. Okay, so axial loading, torsion. Now let's talk about a bending moment. So we have our cross section, we have some axis here, and let's call this our x-axis coming out of the board, and we've got some moment being applied there. Okay, so what does our stress distribution look like? Well, we've got our highest stresses at our outer points, right? We call that C. So right here we have a compressive stress because we're pushing here, and right here we have a tensile stress because we're pulling. So we call that stress sigma. So what else do we learn? So we also have transverse shear. So let's make that a pipe. Let's make that a pipe. So we have some shear force that's going down across the face. Some shear force. So what does the stress distribution look like for here? Okay, so we call something a neutral axis, and for the bending moment, for the torsion, there's zero stress going on at the neutral axis. But for our stress distribution for transverse shear, it looks something like this, right? With our highest being here, where our Q is max, and 0 being at the two edges, where Q equals 0. Okay? So to recap, axial force, and let's draw these QBs here. So we have our moment acting here. So let's pick a point right here. So if we were to draw that QB, we would have two stresses going in. And if we were to draw a QB, say, in the middle here, at our maximum Q, we would have a shear stress going down like that. Okay? So before moving on, there are some great examples in the book, chapter 8, example 8.2 through 8.7. So, like I said in class, read those examples before even attempting to work combined loading problems. Okay, so if we're given a situation like a road sign subjected to wind, we have a combined loading situation. So we'll have, and I'll draw it up on the board, we have lots of different situations that are going on in terms of our loading and our stresses. So we need to use, from chapter 4, I believe section 3, superposition. So we use superposition to, in a way, algebraically add up these components. So let's draw our road sign. So our answer here is combined loading. And this is my favorite chapter in this entire book. So if you see me getting excited about this, it's because chapter 8 really incorporates everything we've learned thus far, and it really tests your knowledge of this subject. So if we have our sign here as being subjected to a uniform wind, we can draw the uniform wind something like this. Okay, so that wind is going to cause a resultant force. So that resultant force happens at the centroid, and we'll call that F. And then because this sign is pretty heavy, right, we're going to have some weight acting down on the sign. So if we draw our axes here, we'll call our x-axis going down. We'll call our y-axis acting in the direction of this force. So our y-axis will be something like this. And our z-axis will be this way. So y and z. So what do we have going on here? Well, we have some weight that's going down, so we're going to have some normal force at this pipe. So if I were to give you a problem like this, I would have to give you the cross-section of this pipe here. And there's a good chance it'll be a hollow pipe, and you'll have to find stresses at both the inner and outer rim of this pipe. Okay, so we're going to draw all of our resultant forces in the positive direction just to make our life simple. And if we sum our forces in moments and that quantity becomes negative, then we know we drew it in the wrong sense. So this weight here, well, we'll draw it in the positive direction. So we'll call this a normal force at x, right? We know that's going to come out positive because we have a force going down, so that force is going to have to go up. But we'll draw it in that direction just to start off with. We have some force here that's going to cause a shear force in the y, right? It's going to counteract that resultant wind force. We can draw a shear force in the z, but if we work the problem, we'll see that that shear force is actually 0 because there's nothing counteracting it in the z. Okay, so if we look at this force, we have some distance from here to here that will cause a moment about the z-axis. So we can call that a moment about the z-axis. So that force will cause a moment about the z. Okay? We have a force y that will be causing a moment about the y-axis. So we'll draw that in the positive sense. So a moment about the y. And we have this force here that's being torqued in this direction that will cause a torque around the x. So we'll draw that in the positive sense. Some torque, let's make that more clear, some torque in the x, right? So if you know these centroid distances, and you know these quantities, and you know this distance, you can solve for those internal loadings that are going on at that pipe. And remember, we'll have a superposition type of situation here where you have to know, is it positive, is it negative, do we add them, or do we subtract them? And don't forget, Q is sometimes equal to 0 for your transverse shear, but we'll get to that in a bit. So if you don't like that wind example, I've got another one for you. So let's take our wooden mannequin here. If you've ever visited my office, you've seen him in the corner, right? He doesn't do much but just stands there. Sometimes students put him in different orientations, but this is my wooden mannequin. So let's call this wooden mannequin Byron. So Byron is a freshman in college. He is going to a party within his first 2 weeks of school, and at that party he and his friends decide they want to start arm wrestling. Completely making this story up, by the way. So he starts arm wrestling. So he's sitting with another guy who is, by the way, much bigger than Byron, and so they're sitting at a table and he starts arm wrestling, right? And so they're locked in pretty hard. So we can draw his arm kind of looking like a pipe. So let's call this Byron, okay? So we're going to model this arm as a pipe. Okay, so let's get the axes labeled well. We've got an x-axis coming out here. We've got a y-axis here and a z-axis going up. So this is Byron's arm. So what bone is this? That's the radius. And that's the humerus. You won't be tested on that, but just for your information. So he is being torqued. So let's add a force in the z direction here. So I don't know, he's arm wrestling someone really strong. Let's call the person he's arm wrestling Russell. So Russell is very strong. So he's applying a force here. So this is like saying his arm is at this angle and he's applying a force just like that. Okay, so what does that cause at this cross section here? So let's erase Byron and let's draw some reactions. So if we draw everything in the positive sense, we'll have a shear force in the z. Okay? A shear force in the z. So all of a sudden, we're arm wrestling, and most of you think of arm wrestling as pure torsion. But we've got situations going on that are much more than torsion. So we've got a shear force going on. Okay? So we have this distance of your humerus, right? And we're taking a chop in the humerus, right? A theoretical chop. You wouldn't want to do that to Byron. Theoretical chop in Byron's humerus at some, say, mid-distance there. So we have a force times a humerus distance, so that'll give us a moment about the x-axis. Okay, so all of a sudden Byron's arm wrestling, he didn't expect it, but he has shear and a moment stress in his bone. So we'll talk about a torsion stress finally. Force times the radius distance will get us some, let's draw it in the positive sense, it'll be this direction. So some torque in the y direction. Okay. So Byron is experiencing a shear, a torque, and a moment. But what if Russell, the guy he's arm wrestling, is not only applying just, oh, I'm breaking his bone already, not only applying a force here, but say he's pushing on his bone a little bit this way, a little bit in this direction. So let's say he's also being applied, Russell is applying a force here. So let's call that force prime. Okay? So this force prime here is going to cause a normal force. So let's change colors here. This is going to cause a normal force, and we'll draw it in the positive sense. So a normal force here, a normal in the x direction, and it's going to cause, let's see, we've got a force here times a distance. That'll give us another torque. So that'll give us another torque in our z direction, right? Or the first torque in our z direction. Let's see if that's correct. Yes, that's correct. So it'll cause a torque, and let's draw it in the positive sense, so a torque in the z direction. So this innocuous activity of arm wrestling has caused a shear force, two different moments, two different torques, one moment, two torques, a shear force, and a normal force in Byron's humerus. Okay, so people, if you want to arm wrestle, beware of the combined loading situation that you're putting your bones through. So we'll put Byron up for now, and we'll wrap up this session with one final example. And this final example is a good, it's a good demonstration of the kind of thing you'll see on your test. Okay, so we like pipes. So we're going to talk about a pipe. Okay, this pipe has a cross section. We'll call this X, we'll call this Y. So we have X, we have Y, so Z is out of the board. So Z is out of the board. So let's say on this pipe we have, let's make it Christmas colors, right? 'Tis the season. So let's say we have a shear force in the X. We have a shear force in the Y. We have a normal force in the Z. Let's say we have a torque acting in the positive Z direction. Let's say we have a moment happening around the x-axis, and we also have a moment happening in the y direction. Okay, so this could be, from our example earlier, this could be a crane hoisting a beam. This could be a woman walking her dog. This could be the cross-section of a femoral neck. This could be any type of combined loading situation we have where we had to take what we were given forces and dimensions, and we have to draw something like this. So you can bet you won't be given this image on the test. You have to produce this image, and from here you can find your stresses. So let's call this point up here, let's call that point A, and let's call that point B. Okay, so let's look at point A. So normal stress. So we typically call normal stress with a lowercase sigma. So what is happening to cause normal stress at this point? Well, at A, we have a normal force in our Z direction over our area. That'll give us a normal stress. Okay? We'll put a plus or minus here because we don't really know whether it's plus or minus, but we'll work those details out as we go along. So we have some moment in the Z direction. So this is, if you can imagine it, we're curling our hand this way. So a moment in the Z direction. So we have an mx times some distance y over I, our moment of inertia. So looking at this picture, is this sign going to be a negative or a positive? If we're calling tension to be positive, we're pushing in a sense, so we're compressing that point, so that'll be a negative. Okay? We have one more component. We have a moment about the y-axis. Okay? So we have my x over I. But if you remember from our picture here, our moment at our neutral axis, right? The stress is equal to 0. So in this situation, we have a moment that's occurring about the y-axis, and our A falls at that neutral axis. So this distance x is actually equal to 0. So that goes away. So we don't need to worry about the sign because that goes away. Okay? So let's look at our shear stress at that point. So we normally call that tau, lowercase tau at A. So what do we have going on for shear? Well, we have a VQ, VXQ over IT. So Vx is going this direction, and we're at the neutral axis of this. So is Q going to be its biggest, or is Q going to be its smallest? That's what we have to ask ourselves when we do this type of problem. So it turns out Q is actually going to be its biggest. So this is going to be our Q max. So what else do we have? We have a shear going in the X direction. So V, Y, I'm sorry, a shear in the Y direction. So Vy Q over IT. So recall that Q equals Y bar prime A prime. Okay? So what is our area prime for this point here with our shear in that direction? You can think of this as the area, so starting at the neutral axis, so we have some neutral axis here, we have some shear, say the shear is going here, and this is our point A. So starting at the neutral axis, we're going up towards our point A. A prime is the area above that point. So is there any area above that point? If the answer is no, then your Q goes away. So your Q is actually 0 because there's no area above that point. Another way to look at it is simply the fact that at the top and bottom our shear stress distribution looks like that. So our Q is 0 here and our Q is 0 there. So the shear stress contribution from our shear force is 0 at that outer edge. So the last thing to look at will be our torsion. So T rho, we can say rho, over J. Okay? So we can say rho because rho means it's our farthest distance, or you can call it C, C being your farthest distance. Rho is some intermediate distance. So our C here is equal to the radius of this tube, or this circular cross-section rather. So we have some torque at Z times our radial distance over J. So that's how you solve for point A. So for point B, you can do the exact same thing and just realizing what's going on where the Q's are equal to 0, where the bending moments are equal to 0, and you can solve it that way. So thank you for joining me this afternoon. Good luck on your final in a couple days, and as always, stay curious.